Dear ladies and gentlemen, my name is Benedikt Waldschmitt. I'm a research assistant at the Institute for Steel Construction and Material Mechanics at TU Darmstadt. I would like to welcome you to this presentation on 3D printing with steel, additive manufacturing of a bridge in situ, on behalf of our institute under direction of Professor Jorg Lange. Among other things, we deal with the application of additive manufacturing in the field of steel construction. In this context, the project of a bridge manufactured using 3D printing on site was launched in spring 2019 and is shown in principle on this slide, in which an industrial robot prints a bridge over a creek using weld. In my presentation, I will first briefly introduce WAM in general. I will then report on the development of the bridge using scaled models and the resulting challenges in slicing, as well as the development of a manufacturing strategy and process. Preliminary investigations based on the bridge models by using computer tomographic scans and investigations regarding the load-bearing capacity will provide information on the performance of the final bridge structure. At the end, I show the manufacturing on site and summarize the most important findings. The first question is, what is WireArc additive manufacturing? It's an additive manufacturing process based on gas-shielded metal arc welding. With a high build-up rate up to 5 kg per hour, WAM offers the possibility of integrating additive manufacturing into steel construction. The wire electrode, e.g. carbon or stainless steel, forms the printing material, which is applied in layers. A system consists of an industrial robot with up to 6 axes and a connected welding device plus corresponding supplies. The right-hand side shows a layer-by-layer material application which extends vertically. In contrast to this conventional approach, our team's challenge was printing a bridge over a body of water in situ, directly on site and as bridges usually span obstacles, we first had to create a corresponding model for cantilevered structures. For the application of 3D printing processes, a suitable division into layers must first be developed for each object to be printed. This process is called slicing. While for conventional additive manufacturing processes, slicing can usually be generated using G-code, we had to come up with our own segmentation of layers. While the left-hand side shows the case of a common slicing and manufacturing direction, the right-hand side illustrates the layer construction for a cantilevered structure. The idea was to first tilt the application direction by 45 degrees to simplify the layer deposition and prevent material from dripping down. Besides, the CMT cycle step process was used, which allows a detailed controlling of the parameter setting to reduce the energy input. Precise information is given in our article. In addition, the welding torch orientation was changed 45 degrees to the horizontal to ensure an accurate hit in the center of the previous welding layer. As a next step, we had to evolve a manufacturing strategy. This describes the sequence and the direction in which layers are applied. As we had considered the challenge of a double curved shell shape, we had to divide the bridge into 3 symmetrical segments with different application directions and layer path, given on this slide. The first segment serves as the basis for the cantilevered second segment and forms a surface inclined by a 45-degree angle to the base plate indicated via the green line. Proceeding from this structure, new overhanging welding layers are applied. To determine each layer path, we use parametric robot programming. This means that the individual segments of the bridge were divided into 100 isocurves, shown by the blue line, which coordinates are determined by polynomial functions using linear regression. This allows the robot to independently calculate the x and y coordinate of a point as a result of the current z height. The completion of the third segment fills the gaps and finishes the bridge. With that, we were able to think about the relevant elements of the manufacturing process. To guarantee a continuous process stability, so that a uniform structure with minimal surface waviness can be achieved, a new manufacturing process had to be developed. For this purpose, it was first defined that the molten material is applied alternately to both bridge halves, so that one side could be cooled to an intermediate layer temperature below 150 degrees Celsius using compressed air cooling with minimal addition of water. Before the layer is applied, the bridge is measured at regular intervals using the Fronius touch sensing method, in which a contact voltage is triggered when the measured wire tip comes into contact with an object and the current position is recorded as a result. The new coordinates are then calculated with the Z height and the application process can begin. This is the base for the parametric robot programming. Next, we turn to the welding process itself, shown on this animation. The start and end point of a weld seam are flatter than the continuously welded area. For the bridge, there is also the special case that the geometry not only protrudes in the longitudinal direction, but also expands in the transverse one. Therefore, additional material must be applied at these points by a supplementary process step. A spot weld at the start and end point before the start of the continuous layer application compensates for the local height loss and at the same time prevents the wire tip from missing the last applied layer. Subsequently, the continuous material application alternates in the welding direction for each welding layer. For a constant travel and wire feed speed, the seam geometry is higher at the beginning and flatter at the end. To avoid propagation at the height difference, both properties are cancelled out by the alternating welding direction. The results described were used to manufacture two bridge models with a scale factor of 1:8. The picture shows the ongoing manufacturing process of one model. It was then examined for the investigation of non-visible defects and the control of a homogeneous material application by means of computer tomographic scans. Lighter areas describe a lower material thickness. The scan data shows a mainly homogeneous material distribution visible in the upper left image. A critical area is the center of the bridge where the two bridge sides meet, shown in the lower left image. To ensure the bond, an additional welding layer was applied in the transverse direction. Nevertheless, it can be seen on the CT scan that this was not done to the same extent to the lower half of the bridge as in the upper area. Another transverse seam could solve this problem. An additional seam applied on the underside would also be conceivable. A closer look shows that pores occur only particularly and mostly in the area of the edges and have no significant influence on the load-bearing capacity of the model as shown in the following slide. In order to be able to make a statement about the load-bearing performance of the bridge, the model was loaded in a universal testing machine until beginning of yielding. For this purpose, pressure was applied by a steel cylinder in the middle of the bridge to distribute the load over a wide area. The steep increase of the load deformation curve up to 35 kN is due to the deformation of a rubber placed in between cylinder and bridge model. From this point on, the deformation of the bridge can be tracked more precisely. The value of the deformation exceeds 5 mm before plastification even begins. For comparison, a numerical simulation based on third-order theory and material properties from tensile specimens were used. For a constant cross-section thickness of 6 mm, a maximum elastic deformation of 1.7 mm was calculated for load-controlled analysis, which thus significantly underestimates an actually occurring deformation. Possible explanations are the assumed constant cross-section thickness and the neglected influence of the thermally induced residual stress occurring during the printing process. This requires further research. Nevertheless, there is a good concordance between the load-bearing capacity determining from the numerical model and the compression. In September 2019, the construction site was set up on the grounds of the TU Darmstadt. First of all, a foundation was built for the robot, and the two base plates of the bridge were anchored back using spin anchor, which are part of a concreteless foundation technology. On the left side, the equipment of the WAM system is shown. In addition, a suction system to reduce the welding fumes were installed. A compressed air-based minimum quantity lubrication system enabled the cooling of the bridge sides. The construction site was enclosed with a tent. On the one hand, this was to protect inconsiderate bypassers from looking into the arc, and on the other hand, it ensured that the shield gas bell was unaffected by wind and weather. The pictures show different time frames during the manufacturing process. On the left side, the first segment is nearly finished. In the middle, the progress of the second section has reached more than 250 layers. Around that time in mid-October, unexpected significant deformations due to thermally induced residual stress occurred. This led to a stop of the construction site. The cross-section of both bridge sides started twisting continuously after the application of 1 or 2 layers, but the welding robot partially missed the bridge when manufacturing next layer. To solve this problem, the manufacturing strategy was changed. To reduce the deformation, the bridge's cross-section was divided into 5 stripes. With that change of strategy, we were able to continue. On the right side, the continuation of the middle stripe, which was printed first, is given. At the last impression, this picture shows the moment of the bridge closing in early November. To summarize our findings, the parametric robot programming is in conjunction with the manufacturing strategy and process makes it possible to additively manufacture cantilevered curved structures. The listed process sequence characteristics ensure a stable manufacturing process. Spot welds in particular prove to be beneficial for this. We performed preliminary investigations on the fabricated scale bridge model, as well as the subsequent CT scans and load capacity tests confirmed the assumption of a good material connection and sufficient load-bearing capacity. A change of the manufacturing strategy was required due to thermally induced residual stress, but it was shown that the in situ manufacturing of large steel constructions on site is feasible. Thank you for your attention.